Alright guys, this is going to be your review for your first quiz, which is on set notation and classifying numbers. It's going to be on Wednesday, September 7th. So the first thing that we have here is directions that say list all the classifications for each number. It's a pretty common kind of problem for this, except that most of the time the only thing that really matters is the most specific classification. But here they want you to I guess, get in the habit of understanding the logical reasoning behind it. So when I look at this first number, I'm thinking about the same kind of rationale every time. I'm thinking to myself, okay, is it a real number? Well, yes, all of them will be real numbers. So now, is it rational or irrational? The judge is to say irrational would be a hard square root or something with a pi in it. So this one is square root of 5, which is not exactly easy. So this one I would say is irrational. So we'd label this one with an R for real, but also we'd have to list that it's an I for irrational. The second one, it's not a pi number and it's not a hard square root either, so it's at least rational. And then the next step down is to say, is it a normal number that's either positive or negative? In this case, it's -4. That's pretty normal. So that's going to be at least an integer, but whole numbers start at 0 and go up. So this one is going to be an integer at most. So I'm going to list it as a real, rational integer. Alright, this is the one that kind of people have trouble with from time to time. It's a decimal that repeats. It is definitely real, but the question is it rational or irrational? Remember, it's not a difficult square root and it's not a pi, so it's not irrational, it's actually a rational number. And because it's got decimals, it's definitely not an integer, so we stop at rational for this one. And the last one we have is 132. Obviously not a number with a pi, and obviously not a hard square root, so it's definitely rational. So we say real, rational. It is a normal number, so it's an integer, and in fact, it's a whole number, and because it's not 0, it's also a natural number. So you have all of those classifications for a natural number. See, most of the time we would just say number 1 is irrational, number 2 is an integer, number 3 is rational, and number 4 is natural. But since the definition and directions say to list all the classifications for each number, we did have to list them all. Okay, for these directions ask you not only to list their classification, but also to order them from least to greatest. Notice that I said just give the most specific classification for each. That means you don't have to write them all out. You can only write the most specific or the last one you would write. So let's talk about how to order these things from least to greatest. Most of the time I would suggest that you convert all of them to decimals, order them, and then turn them back into the regular numbers. You can do that if you'd like, but I would say that it's not necessary to do that for this problem because some of them I think we can figure out right away. For example, -100 over 3, that's almost -34. It's -33.333. So it's really negative. So this one is by far the most negative of all these numbers. So I'm going to list that one first. So we have -100 over 3 listed first. And then the only other negative number is this one, so it must go second. And now it's up to these three numbers over here. Well, I'm looking at it, I know 2 is bigger than 1/8. And when I look at square root of 6, again, I don't know exactly what the square root of 6 is, but I would say that I know square root of 4 is 2, so square root of 6 must be bigger than 2. So if I'm saying 1/8 is less than 2, it goes first, then the 2, and then square root of 6, which what we just said was that the decimal is obviously bigger than 2. So they're in order now. Now it's a matter of classifying them. So when I look at a whole bunch of numbers like this, I look for things that I would know right away. I say anything with a pi, anything with a hard square root, those are irrational numbers. So I'm looking for all these, none of that right here, I got an irrational number. Then I go looking for any kind of normal decimals, any kind of decimal or fraction whatsoever, and I say to myself, okay, anything that's a decimal or fraction, it's not even going to be an integer, it's got to be rational and that's it. So all of these are all rational numbers. And then finally I'm left with the number 2, which I know is an integer because it's a normal number, and it's a whole number, and in fact it's actually a natural number. So this is the most specific classification I think you get. Alright, now I might actually need to do a little work with a calculator to figure out this next one, but it's the same general principle. We want to figure them out in decimal format so that we can compare them, but I want to order them in the format they've been given to me here. So square root of 5, I know it's a little bit more than 2, but let's do the actual decimal. It comes out to 2.23. I'm just writing it up here for reference. Pi over 2, I know, is going to be somewhere around 1.7 something, actually 1.57. Now I have square root of 3, 1.73, and it's negative, so negative 1.73. 1.3 to the bar, it's already a decimal. And negative 1.1 third is 0.333, so this is negative 1.33. It keeps going. Okay, so where's our most negative number? It looks like that's this one. So I'm not going to write negative 1.73, I'm going to write negative square root of 3. That one. Here's our second most negative one, which is negative 1/3. Then looks like 1.3 with the bar over it. Pi over 2. And finally square root of 5. Okay, now that I've got them all in order, it's time to classify them. So again, I'm looking for pi's and hard square roots for my irrational numbers. I got a hard square root right here, that's irrational. I got a pi right here, that's also irrational. And I got a hard square root here, which is irrational. Then I'm looking for any kind of decimals or fractions, because I know that they're not even integers. So decimals and fractions tell me rational. Here and here. That's what's done. All right, on to everybody's favorite, set builder stuff. Set builder really isn't too bad. It's the idea that ultimately you can write this notation for any kind of set. Sometimes it's easier than others. This one really isn't that bad. What you want to notice is that you have two ranges of numbers, one here and one here that we want to represent. So you work on them individually. Every set builder starts out the same way, with an X and a slash. And most of the time, you're going to have a range of numbers to deal with. So I usually mark that range starting out like this. Where we're going to say X is between two numbers, more or less what it means. So I'm looking at this one first, and I'm saying to myself, what is the lowest number that's represented here? Well, if you look at it, it means the most left number. Well, this keeps going forever. So that means it's actually going to negative infinity, which goes here. And then for the other number, I want the highest number this ever gets, which it goes up to 3. We got an open circle there. Open circle means that you don't want to include that 3. So here, I'm going to leave this as a regular inequality without a line underneath. And infinity symbols never get a line underneath. Just like in interval notation, they never get included. They always get parentheses. All right, so I have one range of numbers represented. The other one, I'm going to write an or here because it can be either one, is this side. So again, I have the same setup. I have a range of numbers, but this time 0 is the lowest number. And because it has a closed dot, it gets a line underneath of the inequality. And it goes on forever to the right, which means it goes to positive infinity. We don't include infinity, but we're done with that set. Okay, this time, I think a lot of people get a little bit confused about what it means to say something in words. It means that they want you to describe the numbers that they're talking about in those two sets. So the first one is a little bit tricky because it deals with negative infinity to 3. So a lot of people like to say all the numbers between negative infinity and 3, including 3. That's what the bracket means. But most of the time we don't really talk that way, right? So if you think about it, what does that really mean? It means that you can have any number you can think of that's less than 3, because it goes all the way to negative infinity, and actually it can be equal to 3. So in words, I would say that this first part says all numbers that are 3 or less. Let's deal with the second part, where it says 5 to 11. So we know the number range is between 5 and 11. So we're going to say for the second one, or it can be all numbers between 5 and 11 including 11 but not 5. That's how you say all of that stuff in words. Okay, this time I ask you to write two things that are already ranges of numbers and turn them into interval notation. Usually this is pretty easy to do because interval is just another range of numbers. It's just a different way of writing it. It's also very non-specific. So this one I think is probably easier yet. We always start an interval with a comma, and then we need a low number here and a high number here. So the low number for that range is 3 and the high is 5. Now, there's no equal to symbols here, so that means they are not included in the whole thing. So we represent not included with parentheses. This one might be a little bit more tricky because really what it says is all the numbers from 2 all the way down. So it means you could go as negative 0, 1, 2. We call that negative infinity. That's the lowest number you have. And the highest number you ever get to for this side is all the way up to 2. So it can be equal to 2, so we represent that with a bracket, meaning we want 2 included because there's an equal symbol. And as I said earlier, you never include infinities in anything because it would be kind of impossible to include something that's infinitely big. So you get a parenthesis for that. I put a star next to this one on your paper because I thought it was the one that was probably most difficult. And I definitely got a lot of questions about it today in class, so hopefully this will make a little bit of sense to you. If you think about this from like a number line perspective, it wants you to write all the numbers that are at least or more than 2 units away from 8. So if I'm thinking, okay, on a horizontal number line, or maybe like on the x-axis, all the numbers that are at least 2 away from 8, that would be like 10. Well, 10 is 2 places away from 8. And any number to the right of that would be 2 places away from 8. And on the other side, 6 is 2 places away, plus any number less than that. So maybe on a number line, just seeing it might actually make it easier. If we put an 8 right here, we go 9, 10, 7, 6, 5, like this. And I would say, okay, 2 places away from 8. Well, here's 10, but it has to be more than 2. So it's actually an open circle this way, and it would be shaded that way. Same thing for the other side. 6 or anything less than that is also 2 places away. So this isn't really set notation, it's just a picture of a number line. So I think you guys know how to do number line ones, so I thought maybe showing you it this way might make more sense. I want to write an interval that represents this and this. So let's work with the first one. We know that now that it's going that way, we just did one a little bit ago, going all the way to the left like that represents negative infinity, and an open circle all the way up to 6. Open circle means not included, never include infinity. The other side is 10 is the lowest number, and it goes to the right forever, which would be positive infinity. Never include infinity, and 10 is an open circle, so we end up with this as our answer. So in Set Builder, we started out the same way, and we kind of already have our ranges that we figured out from over here. So we can write this a couple of ways, but this is the one I would suggest to keep a pattern consistent. Low number, negative infinity, high number, 6. There were parentheses here, just like there will be no lines here. And then over here, low number is 10, high number is infinity. No lines underneath again. We're done. If by chance you're pretty savvy with this set builder thing and you understood this pretty well, you could have written this as another possible way to write it. But the first one sticks to the pattern that we've been working with. Either way, they're both acceptable answers. Okay, this time we're asked to write positive multiples of 5, not including 0. I told you guys before that there's a pattern for Set Builder that you always follow, and that this one was really the only exception that you were going to see to that pattern. See, anytime you see multiples of 5, what that means is I want to take x and multiply it by 5. So I'd write it like this. And actually, before I go any further with this, I want to go over to the roster side of this thing. And we'll come back to the Set Builder in just a second. Remember, roster means to list all the numbers possible. But if you think about it, the positive multiples of 5, well, that's like 5, 10, 15, 20, 25, 30, 35. It keeps going forever. There's a whole bunch of them. It's infinitely big. So this is the one exception to roster notation, which is that if you can show a pattern in the numbers you're trying to write, you could write it that way. So I want to start with 5, 10, 15, 20, 25, and then I'm going to show the 3 dot thing and close it. That shows that my pattern continues in that same fashion. All right, I want to come back to the Set Builder now. See, right now, this Set Builder says, okay, as long as you put a number in for x and multiply it by 5, you'll get one of these numbers over here. But if you think about it, that's not really true. We only want to multiply 5 by very specific numbers. We want to multiply 5 by 1, we want to multiply 5 by 2, 5 by 3, 5 by 4, and so on. So it's kind of like, what do I call the numbers that I want x to be? Because not only do I want it to multiply by 5, but I want them to only be 1, 2, 3, 4, 5, and so on. So that group of numbers that starts with 1 and goes up very easily like that, it's called natural numbers. So I want to say x, and I'm going to use that mathematical symbol epsilon to say has to be. So x has to be a natural number. Now I'm done. Because now what I'm saying is I want to multiply x by 5, and I only want x to be a natural number. So if I chose, say, 10, 10 would be okay, because it is a natural number. I put it in for x, and I get 50, which is a multiple of 5. But see, if I chose some number other than a natural number, say like 2.2, well, when I put that in for x, I get 11, which is not a multiple of 5. It would be incorrect. So we're specific to say we only want those natural numbers, because those are the only ones we can substitute in for x and get these numbers over here. And it's just a little bit tricky to understand that, but one nice thing is that anytime you have multiples of a number, you always know it fits this format, and then it's just a matter of whether or not you want to include 0. If you do, you want to include 0, then you've got to put x as a whole number. But if you don't include 0, like this one says, and you put x as natural. All right, last one. Last one says all natural numbers from 1 to 7, including both 1 and 7. So I see they're specific. It says only naturals. It gives me a range. Then it tells me to include both of them. All right, well, let's look at roster notation. That means list them all. So we only have to go from 1 to 7, so we don't have to worry about showing a pattern. We can literally just list all of the natural numbers from 1 to 7. Let's think about interval for a minute. I noticed on some of your papers and so on, I saw this as an answer. I saw 1 to 7, and then include both. I saw that. All right, it actually looks pretty good. It does take care of the range part of 1 to 7, and it does take care of including them both. But what it doesn't take care of is the natural number part. See, intervals designed to be for very, very basic and non-specific sets of ranges, sets and ranges of numbers. So as soon as you say natural, it becomes impossible to write it as interval notation. See, this one does not limit it to just 1, 2, 3, 4, 5, and 7. Everything that's a decimal in between 1 and 7 is also part of it. So technically this is not correct. In fact, the answer to this is that it's impossible to write. And now see, Set Builder, I told you, works for everything. So you know that it's going to work. The question is how to write it to make it work. Well, let's deal with our range of numbers. So like usual, we have a range from 1 to 7. We want to include them both, so I want lines underneath of each one of these inequalities. But see, this, again, just like the interval, says just from 1 to 7, including both. It doesn't say anything about natural numbers. But you can add Set Builder, you can add a notation. So just like we did a minute ago, we're going to put x has to be a natural number. Now we close it, and we're done with it. Right, if you're watching this review, I think you've pretty much got everything you possibly see on your quiz tomorrow. It should be about this length, maybe even a little shorter. But you should know how to do roster, interval, and Set Builder to be able to kind of convert between the three things, and also be able to order and classify numbers. If you need help, you can always come and see me, homeroom period. You can find me in the hallway on the first floor during first period, or if you can, 6th and 7th. Have a good night, guys. Take care.